So those who were here last time in the virtual space of 2020 might remember my talk called Module Theory and Query Processing. If you don't remember, that's totally fine. I won't hold it against you. But this is basically the follow-up to that. This is like the full version of what we were doing back then. So we're going to combine query languages and algebra. So think about what do we want from a query language? Well, here are three things we might want. We want it to be efficient. We want to execute efficiently. We want it to be expressive. We want to write down, express the transformations of data that we want to think about, and then we want it to be reasonable, both in the vague sense of being like reasonable, but also something that we can reason about. It's like something that we can say, well, this query is equivalent to that other query, things like that. And it can be hard to reconcile all of these three concerns. Our approach is that if we use algebra, in particular with a categorical viewpoint, then we might actually be able to achieve all of this. So let's see what's going on. So let me start by talking a bit about algebra. And by algebra, I mean two things. I mean the branch of mathematics called algebra, and I also mean the specific algebraic structure called an algebra. It's like one of the hardest problems in computer science is naming things, but the mathematicians are not always doing so well either. And also we also disagree with mathematicians about what a module is, but that's another story. So this is the mathematical notion of a module, which is something that has a zero and has addition, which is associative and commutative, and then it has scalar multiplication. So it's a module over a ring K. And we have the ability to multiply any ring element onto an element of the module to get another element of that same module. So in other terms, it's like an abelian group with this extra operator of scalar multiplication. Usually you know them as vector spaces, but the usual definition of vector spaces is that the ring has to be field. We don't require that here. We just use arbitrary rings. And then what's going to have a module, we can extend that to an algebra, still over ring K. An algebra has the structure that we have multiplication of arbitrary elements between elements of the algebra, which is it should be compatible with the scalar multiplication and just distribute over plus. So it's what we'll know as a bilinear transformation. And then finally, if this multiplication operator has a unit, a 1, then the algebra is called unital. And we'll see some of our algebras will be unital and some of them will not be. And the question of whether it is actually quite important.
But you insist on associative.
I insist on what?
You insist on associative.
Yes. And also commutativity. So it's actually, I guess some would explicitly call that a commutative algebra structure.
Are you using that two-sided module?
Yes. Everything is commutative, actually. That's just probably the easiest way to say it. Everything's commutative in this today. Okay, so let me present some particular way of constructing modules. And we'll take a very kind of abstract approach, the kind of universal algebra categorical approach. We'll just say, well, what are the properties of these different modules we want to work with. The simplest one is the scalar module, and we can think of it as being generated by just the element 1. It's like it's 1, and then it's everything that can be reached by scalar multiplication, which of course in the scalar module is everything. So in other words, if we want to define a map out of the scalar module, then all we need to say is what happens to 1. And then that extends uniquely to a linear map, because everything else has to be, like if you say f of 3, then that has to be 3 times f applied to 1. So f of 1 is all we need to know. Another way to say this is that this maps from scalars to some module is isomorphic to that module, because picking a map from scalars into the module is the same as picking an element of that module. Okay, so that was the easy one. Now we take the well, the scalars are kind of like the nullary tensor products. Now let's look at the binary tensor products of modules U and V. Yeah, by the way, I'm using U and V because I'm kind of alluding to like pretending that the vector spaces, like the nomenclature, so I'm using M. So the simple way of saying it is that, well, it's generated by elements of the form U tensor V, subject to the condition that the tensor constructor is bilinear. But you can also, I mean, basically I'm using the same definition as Fritz used in the first talk. And the algebra structure, well, supposing that U and V have algebra structures in the multiplication, then we define the multiplication of the tensor space by just component-wise multiplication. And to define maps out of the tensor product, well, we just need to define a bilinear map. So I'm running this in the curried way, just to save like having to define what a bilinear map is. We just iterated the linear maps. And again, another way to say this is that we can characterize the homomorphisms by saying, well, mapping out the tensor product is the same as mapping out like separately from each space. Okay, so at this point you might be thinking, well, okay, what does this have? Like, how can we get anywhere near query processing with this? Okay, so now we're getting closer, because the free module. So now we have a way of injecting sets into a theory. So take some set A, like think of this might be the set of strings or something, like a set of dates, something that you want to model, and then we're making the free module over that set. Generated by elements, so it's take some element of the set and put it in these brackets, and that's like a singleton. And then it's just again freely generated over that, so we get sums of these singletons. We can multiply with like 3 times A plus 2 times B, and it's like the kind of elements that we have. And here's where the multiplication structure gets a little bit interesting, because what it does is it takes. So again, it is defined by its action on the generators only. So if we have like multiples and so on, it will just respect that because it has to be bilinear. And if we get 2 of the same element, then we return that element. If we get 2 different elements, then we get 0. So this is kind of an intersection operator. And the elimination principle says that, well, to define a map out of the free module, all we need to say is what happens to the generators again, which is, we have to. So if we have an ordinary map, like this should be a linear map, like a sub 1. The notation I'm using, this should be linear. The point is that the F is a normal map of sets, and the induced map is a linear map. Which is, well, yeah, it's written correctly down here. Linear maps out of the free space is the same as maps out of the set into the the set of elements of the target space. Now, the problem is that this free module does not have, in general, a unit element. I mean, if it's okay, so if the generating set is finite, then we could define the unit element as just the sum over all of the generators. We can write it as a finite sum, and that will indeed be the unit of the multiplication operator. But in general, we'll have infinite sets like the set of all strings. So we don't have a unit, so we need to add one. And we literally just do that. We just define the compact free module. It's like there's a free module that's been like undergone compactification. We join this unit element, and then we just kind of stipulate that it is a unit element by just defining equations with no extending a multiplication, just saying, well, when we multiply with this unit element, which we call star, it's kind of the wildcard element, and it actually behaves as a unit. And the elimination principle has to be extended accordingly. So when you map out of it, and if you want to write a module, a linear map out of this, then you need to specify what happens to this wildcard. And again, and the homomorphism characterization is extended accordingly. Yes. So again, it's linear maps because actual, I'm not talking about the algebra homomorphisms because that's a very restricted notion because you have to preserve both multiplication and units, and that's too restrictive for what we're going to do here. So we won't actually be using algebra homomorphisms. Okay, so here's yet another construction. It's kind of a generalization of the free modules. So these can, I call this a finite map module. So here we're given a set and a module, and generators are kind of, we take a set element and then an element of the module, and then we have these kind of primitives that A maps to U. So think of this as like any given finite map can be written as a finite combination of these, like this key maps to this value, this key maps to this value, and so on. And the multiplication is defined similarly to the free one, but in this case, it's actually, when we have A maps to U and A maps to B, then we have to multiply the U and B, so kind of recursively, for it to make sense. And the elimination principle is extended accordingly again. So we need, so instead of having just from A into B, then we have A into and then a linear map from okay, yeah, that should be linear as well. Here from U to B to be a linear map, U to V. And again, we have the same problem as we had with the free modules, but there's no unit in general. So we have the compact maps here, again, by just adjoining the unit. So in this case, it's like, it looks like elements that have wildcard arrow U, which is kind of like, again, the sum of all possible generators, but it's like, it's a symbolic element. It doesn't, again, even when a set is infinite, it's still kind of, it just symbolizes the idea of the infinite sum. Okay. So let's see. So given such a compact map, we can define what it means to look up a value. So given we have from A compact map to U, and then we want to look up some specific key in that map. So we can define that by just saying, well, again, it's a bilinear operation. It's linear in the map, and it's linear in, well, it's a linear operation, right? It's linear in the map. So A matches to A, and then we just get the element. If it's different, then we get 0. If we look up, right, so if we look up the wildcard in the map that just does an A, then we don't get anything. But if we look up an A in a wildcard mapping, then we get that value because it always matches the wildcard. And if we look up wildcard, we get the value. It's kind of like, so any element matches itself and it matches the wildcards when we're looking up. So as an example of what's going on here, consider this element like wild maps to 2, A maps to 3, and B maps to -2. Just to make the point, we can have negative multiplicities. So if we look up wild in this X, then we'll get 2 because that's the multiplicity of the wild card. If we look up A, however, then we'll get 2 plus 3 because we get 2 from the wildcard plus the 3 from the A mapping. But if we look up B, however, then we get 2 from the wildcard minus 2 from the B mapping, which results in 0. So B is actually not, in some sense, not in this map, even though it's mentioned in the list. And if we look up some unrelated element C, then we'll just get 2. So this kind of works like, when you have a kind of a finite map with default values, but it's different because this wildcard is not just the default value, it's kind of a baseline value that's added onto anything else. So the individual mappings specify how much we deviate from that baseline value given in the wildcard. Okay, so I presented I don't know what's like a gaggle of modules. I don't know what the collective noun is for modules, but there's different module constructions here. Many of them are related in various ways. So here are a bunch of isomorphisms that we can write down. And well, if you study this a bit, you might get the idea that every one of these constructions are actually secretly just free modules, because you can apply these one at a time and then finally reduce the free module of some set. And this. So the question is, all these is free modules, and the answer is, well, yes, but no. It's true in the sense that there exist isomorphisms for all of these, but it's false in the sense that we're better off if we ignore that fact. So it's well, Yeah, let me just proceed to the point of why, for instance, this might be a bad idea. So consider this isomorphism between the free module over products, which is isomorphic to the free module over each of the sets, and taking them with the tensor product over these. Take some element of the tensor product, something like this. So we can write elements down like this. So we have like some sum of basis elements, and then tensor another sum of basis elements. And let's consider what happens if we transport it via this isomorphism. So first from right to left, the isomorphism. Well, so we're converting each. Well, to actually apply the isomorphism, we would have to expand this tensor constructor bilinearly, because we want to reach the base case where it's like a generator times a generator, because then we can construct the pair that we need to have elements of the free space over the product. So then we have to reach something like this, when we're actually listing each of the combinations. So we have three, a sum of 3 and a sum of 3, so we get a sum of 9 pairs. And then when we go back again from left to right, well, I mean, there's kind of no other way to do it than just we're just doing it by each component. So then now we've expanded. So this term is equivalent to this term, of course, because we're not really doing anything, and yet we're actually doing a lot of work here. It's like this is yes, question?
Yes, don't you have to do this expansion anyway as soon as you try to use X for anything?
So that depends.
Like your module is generated, but these pages like bracket tensor bracket things.
Well, so the thing is, it depends on what you're using X for. So if your application, so the thing, if you want to use X for something that essentially uses it as a free module, then yes, but you might do, for instance, a projection. I'll show you in a minute what that means. So maybe we're just interested in the A's and we don't care about the B's. Then we'll actually be able to just examine the B's once, because we want to tally up how many of them there are, but we don't actually need to make all the combinations.
Okay. Yeah.
So yeah, but good question. Let's see. Okay, yeah. So that was the algebra. Now for some query languages. So I'll present kind of Rosetta Stone between SQL, relational algebra, and algebra. So SQL, I think of that as having a kind of mixed set and multiset semantics, because it's like, well, you can have multiple copies of the same row, no problem in SQL, but some of the operators will kind of implicitly do duplicate elimination. So you have to be very careful in SQL if you're thinking about like sets versus multisets, because you can get surprised. And also updates do not commute, and by that I mean like insert followed by delete is not the same as delete followed by insert. It's like that's how SQL usually works. Relational algebra has a pure set semantics, and similarly updates, I mean in the sense of set difference and set union don't commute. And then our system, which I just called algebra, the semantics, which kind of set we're working on depends on the choice of ring, the K. And then I suppose the other two updates do commute. So if we add something by just saying plus this thing, and we delete it by saying minus this thing. And so whether we add it and then delete it, or delete it first and then add it, it doesn't really matter, because plus is commutative, which is great for like not having to synchronize your database. Unless you, of course, I mean, you can do it at select opportunities, but like in general, you're not forced to check if something exists before you add it or delete it. You can just do it right away. Okay, so let's look at the choice of rings. If we have like a finite field of 2 elements, then it kind of looks like sets. The module, like the free module of some type is basically just sets, subsets of that type. If we have the natural numbers, then so in this case it's actually semi-modules, not actual modules. But that would be multisets. And then for integers, which is kind of our favorite ring for this theory, we call them polysets, because it's, well, like multisets but cooler, because you can have negative multiplicities.
Which rules fail?
Pardon?
Which rule fails to be a semi-module? Which
well, so the rule that fails is that a module is called, like it's called a K module, where K is a ring. So it's actually, so the failure is for the natural numbers to be a ring.
Oh, right.
It's only semi-ring.
Of course.
Yeah.
Does that mean when you try and do deletion, it's not going to commute, right?
Yeah. So this semi-module, like you take the theory and just restrict the semi-modules, and you'll have the same problem with non-commutative
Yeah, we're going to
objects.
change green for moonlight.
Yeah.
Anyway,
All right, so that's
Okay, are we good? Okay, and then finally we can take something like real numbers, and that will be like generalized fuzzy sets. And the fuzzy sets is like, well, from 0 to 1. In this case, it's just all the real numbers. We haven't explored this too much, like exactly what it means, but you can do it. Okay, so selection, which is what is called in relational algebra, is basically what in functional programming is called filter. It's like select from some table where some condition applies. In relational algebra, it's like, well, we take the subset that satisfies this condition, and then how do we encode this in our system? Well, we define a function from, so in this case, we think of it as some free module, and then we define a linear map, which just acts on the generators, and then it preserves the generator if the condition is true, and just sends 0 if not. Projection is in SQL, it means you're selecting a subset of the columns that you want to look at. So just like this example, you're selecting one attribute from some table. In relational algebra, it would be like the projection from the Cartesian product of some sets. So you're just saying, well, the set of all y, where x, y is in the table. But be aware here that also something happens to the cardinality when you do this in set theory, because you might have elements that are only, you're throwing away the x's. So you might have elements that only differ in the x value, but they have the same y value. And then when you project and you only keep the y's, and because of set semantics, you actually collapse and you forget that you have multiple copies, which is, it might be what you want, but it might also completely not be what you want. At least in our system, you get to keep your multiplicities when you project away. And this is kind of necessary because everything is supposed to be linear. And another way of thinking about linearity is that we're preserving multiplicities. Way to look at it. So to actually define the projection, we need to do something about, so we want to take, U cross V, and we just want to keep the V, but we have to use we can't just forget that the U is there. We have to do something with it. So what we do is we count it up. We define this count function on 3 modules, and this sends every generator to 1. So we're at least leaving some kind of trace of what was there. And this is incidentally also, this function is what if you're writing, count in SQL, this is what you get in our system. It's kind of implicitly summing up over columns that you're forgetting. Okay. Union is, well, in SQL you have 2 different operators. You have union and union all. So union is the one that, union, and then it's just that it filters out duplicates, whereas union all actually keeps multiplicities. Someone recognized that that's actually what you need sometimes. Relational algebra, well, there's the union operator in our system, that's plus. Cartesian product in SQL is like you just write table 1 comma table 2. Usually people will, well, I think database experts might run away if you actually try to write this down, because they'll, oh no, you're taking like one big table, another big table, and you're making the cross product. So then you'll have like 1,000,000 times 1,000,000 elements in the output. This sounds expensive, right? Whereas in our system, well, that's a tensor product, and as I just mentioned before, we don't want to have any obligation to expand this out. Like depending on what we're doing with it, well, we probably will refrain from doing that, from materializing this. Yeah, so that's why we're just beware of the expression swell. It's going to happen. Intersection is, well, again, there's an intersect operator in SQL. It's kind of like the set operator. And then another way to do intersection is to take 2 tables with the same schema and then take their natural join, which is actually corresponds more closely to what our intersection operator is, which is just the algebra structure multiplication. Because, well, how to explain this? Well, also, so if you take table 1, join table 2, then in the output you'll only have the elements that are actually in both tables. But if you have multiple couples of a given value in a table and multiple couples of the same value in another table, then like 2 couples in one table and 3 couples in the other, then you'll actually have 6 couples in the output. Even in SQL, it's like, so just to argue that our intersection semantics are not actually that weird, because you can recover them just from standard SQL semantics, except that in our system we have efficient representations by just saying this many times this row, whereas in like typical SQL you just get that row listed like 1,000 times, so how many you actually get. Okay, and then finally, if you want to do a join on some attribute, let's say like there are 2 tables and they have a common attribute, so we're doing a join on that. Forgive me if there's an error in the SQL syntax. It's been a while since I actually used it. It should be clear enough what's going on. In relational algebra, we'll have to, it's only the natural join and it works on the names of the attributes. So you'd have to do some kind of, typically, you might have to do some kind of renaming. So I'm calling it alpha 1 and alpha 2. There's shuffling around the names to line them up so that you're joining, so that the common names are those that you want to join on, and all the other names are distinct. And in our system, there's kind of a similar juggling that you have to do, because, well, so we don't have a dedicated join operator. We have this intersection. So what we do is that we have, so if we have, say, one table has A and B, and the other has B and C. And then we want to inject them into a common type. And so what we have to do is that, so for the AB, we have to add a C. And we do this by saying, well, so A comma B maps to A comma B, and then the unit element. So it's kind of the, it's the wildcard for the, which is why we're using the compact tree modules now, because we need this wildcard to actually be able to embed it into this larger space. In a way such that the C component will actually match anything that comes from the other table. And similarly, we set the B comma C to just 1 comma B comma C. And then finally, we can combine that and just say, we'll apply the renaming to the tables and then take their intersection. And then that will actually, in practice, what it will do is all the A's will be kept because they just match the 1, and the C's will be kept because they match the 1, but the B's will be compared. And we'll only keep the ones where the B's match. And this way we get the same behavior. Yes?
Why do you make the B module in the middle also the compact? You don't.
Why did I do that? Yeah, I guess we could actually, yeah, I guess we could dispense with that compactification there. I guess just to make it like uniform. Yeah, I mean, there's kind of the variations in this theme, because you can also, like in principle, you could also, you could also say that even like in this one, you don't need the compact for the C's, say, and you can actually define a slightly more general operator, intersection between a compact free and a free, and then you know that the result will always be a free one, because one of them always has a specific element, and so there'll never be a wildcard in output, because that only comes from 2 wildcards. So yeah, you can make this you can sharpen this a bit actually with the types. Okay, so that was the Rosetta Stone. Finally, I want to talk a bit about how to evaluate, or I call this simplify, because, well, so the question is what do we actually mean in this case? Because I mean, so we don't really want to necessarily just compute canonical forms all the time. Depends on what we want to know. So for instance, if we just want to know if the output is 0 or non-zero, that's kind of like, if you can use this to encode, say, SAT-like problems, and then maybe all you're interested in is there a solution or not? And then that corresponds to checking if the output is 0 or non-zero. And in this case, for instance, if we have something that looks like A tends to B, then we know, if you want to know if that's 0, then all we have to do is check each component separately for zeroness. And we don't actually have to perform this to materialize the full product to know whether the tensor product is 0 or not. So this is why I think it's a bad idea to like separate the idea of evaluation and observation, because the kind of evaluation depends on the kind of observation that you're doing. Another way would just be to say, well, okay, we have to dispense with all the multiplications, but all of it, like all the constructors are fine. And then finally, like the strictest one would be, well, we want it in the shape of a free module, and we want a complete list of all the generators and multiplicities with no generators listed twice, so we know exactly what's in there. That'd be like if you're just running a query and you say, give me a list of all the results and iterate over them. Okay, so yeah, I have 2 slides. Is that okay? Okay, sure. Okay, so the simplification procedure is so how to say this quickly. So when we have the finite maps, then they're indexed by some set, and by these isomorphisms we can reduce that to simpler modules that don't include finite maps. And using this method, we actually recover the idea of generic tries, of lookup structures that can be built in linear time and for any type. And then finally, using that, we can like tackle the hardest problem of this, which is if you have a product of sums and we want to reduce that to a sum of products. And we do that by recursion on the type rather than the expression. So it's like we're eliminating one attribute at a time rather than eliminating one multiplication at a time. And by rewriting like this, you actually get an algorithm that corresponds to some of the strongest evaluation algorithms in databases that can deal with cyclic joins efficiently. And it turns out to be what's known as worst case output optimal, which means that it's not necessarily super optimal, but it's best, like it's as good as you can reasonably expect it to be, is like technical definition of what it means. Okay, so thank you.